But let's start with this one. It wasn't the top ranked one, but I liked it a lot because it came with a picture, and it was from Jennifer Kearns-Lechner, who says, what do you think is going on with this nebula? How does that ever happen? Well, I'm sure most of you know that what we're seeing here is the end stages of nova or supernova. That gas cloud is called a planetary nebula. That's what astronomers call it, as opposed to more like a gaseous nebula. In astronomy, we really have two different classes of nebulae, although they really are just different stages of basically the same life cycle. What's happening here is that star in the center is dying, and it's throwing off masses of its outer atmosphere and its surface out into space, and it's blowing out this giant bubble. Now, usually, these bubbles are more or less round, and that's where it got the name planetary nebula, because the first astronomers looking at these things through telescopes, they just look like little dim disks. They look like distant, dim, round planets. So that's why they call them planetary nebulae, although this one's obviously not very round. Sometimes the star will shoot out these two lobes like this. It's got something to do with the rotation. It's also got something to do with the actual way it explodes. I'd be willing to bet those are on an arc off sideways, and I'd also be willing to bet that this is a cross section, that in fact this is not a two-dimensional thing so much as we're looking at it two-dimensionally, that it's more like a torus, I would imagine, than these two lobes. Sometimes they do shoot off lobes, though. So it's just a particularly exaggerated example in terms of its sort of symmetry. But this kind of thing is fairly common for large stars. So this is somewhat different than something like the Orion Nebula, let's say, although, as I said before, it's all part of the same life cycle. Basically what happened was when the universe was created, the first stars were all hydrogen stars. They were all red stars, bigger and dimmer temperature-wise, although there's still thousands of degrees, but much dimmer than today. And so this whole population of stars, these initial stars, lived out their lives, burned their hydrogen, fused it into helium and some other heavier elements. And then at the end of their life, when they run out of hydrogen, they start burning some of the helium they've created. That's a lot more energetic. The star gets hotter and so forth and so on. And ultimately, these larger stars anyway, the novas and supernovas, explode. And as they explode, they push this gas out into space. And over time, this gas dissipates and then under its own gravitational field reassembles. And then as it reassembles, it looks more like the Orion Nebula. It doesn't have this kind of structure. It's the result of several stars that have previously exploded. But this particular gas lobes that you see coming off of this star have more heavy elements in them than the original star had to begin with. In other words, the gas that's coming out of this dying star has elements that weren't there in the gas that formed the star billions of years earlier. The star made the heavier elements using fusion. It's one of the oldest, most hackneyed things in the world, but it's also one of the coolest things in the world. It's been said so many times, I'm actually embarrassed to say it because it's almost a little too hippy-dippy. But the fact of the matter is it's true, and it's also awesome. And that is that everything you see and touch and feel, including ourselves, all of this was manufactured inside of stars. We genuinely, truly are stardust. We genuinely, truly were. Those heavy elements that make up the carbon and iron in our bodies, and all the iron and carbon and silicon and everything else, was created inside of first generations of stars that exploded, coalesced into second generations, and so on. So that's an astonishing thing, really. That's absolutely astonishing. And one of the many things about astronomy that give you so much perspective. We have a great question about that perspective thing coming up. One of the other couple little things that I might just mention about this picture, just for those of you who like hearing these kind of things. The first thing is that this is enormous, absolutely enormous. Certainly much, much larger than I would imagine than the solar system. Most of these are very, very big. They're large, large, large clouds of gas and dust. That's number one. Number two, and this is something that nobody seems to realize, certainly as much as I loved Wrath of Khan, these guys sailing through clouds, is just not true. What you're seeing here, including the Orion Nebula, which looks very dusty and very kind of thick and milky, even if you look at the densest of these nebulae, you have to understand that you're looking at objects that are light years across and light years deep. in the middle of that nebulae, it's much better than the best vacuum on Earth. The densest part of this picture is many times scarcer than the best vacuums that we can maintain on Earth. So even though it looks kind of dense, and even though the real deep, dusty, nebulae with a black kind of look to them is much, much, much thinner than a really good vacuum on Earth. You're looking at light years of density, of depth. So that's the second thing. And finally, the third thing I'll say, and this is really disappointing, I'm sorry to say, but that is that whenever you look at these beautiful pictures of these nebulae and you see the incredible images that come from Hubble and you see the Orion Nebula glowing red and blue and all this other stuff, and you think if you had your telescope out, you'd be able to see all this stuff, but you just can't. And I'm quite sure that even with the biggest telescopes in the world, you can't. These are the results of time exposures. And sad to say that the Orion Nebula, which is beautiful, through a telescope is just essentially a slightly gray-green smudge. The bigger the telescope is, the more detail in the smudge, the more of it you can see. The darker the sky is, the more of it you can see. But you don't ever see through a telescope what you see in these images. And that, I have to say, is heartbreaking. And I suspect, I'm quite sure of this, even if you got close to them as you do in these science fiction movies, if you sailed right up against these things, you wouldn't see the brilliant reds and yellows and oranges. You'd just see slightly less gray than black space. That's how thin they are. So in some level, when we talk about space exploration, so much of what we see and so much of the settings that we set our space operas against, it's not only a question of not being able to get there, it just doesn't exist. Those clouds don't exist in that kind of density. You see these guys sailing through nebulae and banking and turning through the clouds of dust and all this. No, sorry, no. It's just not there. And even if you were right up against the Orion Nebula, the Orion Nebula is 1,400 light years away. It's a long way. If you were 20 light years outside of the Orion Nebula, it wouldn't fill the sky with this giant glowing red spider that we're all used to. It would fill the sky with a giant gray-green glow, maybe like a weak aurora. Hate to be the person to break that to you because it sucks. It's just bad news. The Andromeda galaxy, which was called a nebula because in early telescopes looked just the same little smudge. The Andromeda galaxy is the nearest large galaxy to ours. We have two satellite galaxies called the Magellanic Clouds, the only visible in the southern hemisphere. Tiny little irregular dwarf galaxies that orbit the Milky Way. But the next closest big galaxy is the Andromeda galaxy. It's larger than the Milky Way. It's the largest galaxy in our local cluster. That's 2.5 million light years away. But when you see it through a telescope, it's just a little smudge. But if you could actually see the full extent of it, it's much, much wider than the moon. I think it's something shocking. It's something like 5 or 6 lunar diameters or something. It's just huge. But we can't see it. And if you fly right up against the Orion Nebula, got real close to it, like in that Star Trek episode where they're heading towards the Orion Nebula, you see it out in space. Well, you're in space, so of course it looks like the pictures. No, it just looked like a gray amoeba, just a gray, smoky little dust cloud. Because how do we know this? Well, we know this because we know that galaxies don't look like our time-lapse pictures of galaxies if we get close enough to them. And the reason we know this is because we live in a galaxy, and we see the inside of a galaxy every single dark night in this planet, and it doesn't look like that. The Milky Way is the cross-section of our local galaxy. When I was teaching astronomy in the Miami Planetarium when I was 13 years old, I think I came up with this analogy. I said, it looks like a pancake, and we're inside the pancake batter. If you imagine yourself inside the batter of a pancake, you can look around sideways. You look up, it's clear. You look down, it's clear. But you look around sideways, you see nothing but pancake and a band around the sky, and that's the Milky Way. And the Milky Way, as you know, is just a very diffuse glow. Against a black night, it's impressive and stands out, but it's not what you see in the time-lapse pictures. So that universe doesn't exist. It's not like we can't get there. It just, you're looking at time-lapse photography, long exposure photography. So, sorry to break that to you. Anyway, that's an interesting little picture. Thank you, Jennifer Kearns-Lechner, and we liked it so much that I decided to take the next question from Jennifer Kearns-Lechner.